There exists things you would cut that are pre-cut. So,
okay,
I'm going to do a demo with an onion, which I happen to have.
Which I see.
I happen to have in my office here.
I actually was wondering why there was an onion here in the office. You know.
Just take me a second.
Okay.
All right, you might remember plotting coordinates.
Well, that definitely.
X and Y.
X and Y.
Okay?
Right.
So Descartes sort of pioneered how you put numbers on a graph.
I think, therefore, I am, dude?
That dude.
Get out.
That's why it's called Cartesian coordinates.
Get out of here.
You did not know this?
No, I didn't.
Yeah, he was a brilliant guy, brilliant philosopher with a dose of math.
With a dose of math?
Yeah.
I guess that makes
René
sense.
Descartes.
Yeah, a lot of philosophers were scientists back then.
Yeah, they didn't have the word scientist. They were called natural philosophers.
Natural philosophers.
Right. You were philosophized about the natural world.
Right.
And Newton was a natural philosopher. Today we would call him a physicist.
Right.
All right. If you have a dot somewhere on the chart, you can say how far along is it on the x-axis?
Right.
And then how far along is it on the y-axis? And that dot can be represented by two numbers.
Great.
Okay?
Right.
Anything on a flat surface, its position can be located by just two numbers.
Right.
Okay?
Okay.
Now, if you're down here, then you're in like negative space. Could be like -5, -6, whatever.
Right.
Or negative and plus, or plus and negative. So 2 dimensions can always be localized by 2 numbers.
Okay.
We would come to learn that Cartesian coordinates are not always the best way to think about a problem. Suppose your object that you're trying to describe is not rectangular, but suppose it's a circle.
Right. Okay.
So if it's a circle, let's draw a circle on this Cartesian X and Y axis. I can draw a circle and I can say, what are all the points on that circle? So I can pick a point. Well, I have to measure it. I get 2 different numbers. I pick another point on the circle. I get 2 other numbers. Right? So I have a whole bunch of numbers. I can trace out that circle with all these numbers. Or I can say it has radius r.
Interesting.
From the center.
From the center. So if I
that
plot
1 r
right.
is every point on that circle. Depending on the need, you will choose a coordinate system that makes the problem easier than it otherwise would be.
Sounds smart.
So, in calculus class...
Okay, now I'm checking out. You had to go with the calculus, didn't you? Oh, brother.
So, let me just get a can here.
All right.
This is a cylinder.
Cylinder, right.
There's something called cylindrical coordinates.
Okay.
You know what that is? It's circular coordinates in 2 of the dimensions and rectangular coordinates in the 3rd dimension. Right. If you combine a circle with rectangular coordinates, you extrude
a cylinder.
A cylinder.
That makes sense.
Yeah.
Yeah.
Yeah, it's very cool.
Yeah.
And so let's say we have a potato.
All right.
And you want to make French fries.
Okay.
From scratch.
I'm all about it.
Okay.
Yeah, let's do it.
There you go.
Yeah.
All right. No, let's start with potato chips.
All right.
Look, the potato is in 3 dimensions, and potato chip is what?
2 dimensions.
2 dimensions.
Because it's flat.
It's flat.
Yeah, it's just
flat.
a little slice of potato.
So you take a potato, just slice. Every slice gets a... You turn 3 dimensions into 2 dimensions. You got that?
I'm getting hungry.
Okay. And that's good. It was easy.
Yeah.
Okay. Now you want to make French fries.
Right.
So 1 cut is not enough.
No.
Because a French fry is only 1 dimension. Length. Obviously it has thickness, but let's not worry about that. You want something that only has length.
Right.
You cut off 1 dimension that previously gave you your potato chips, but now you got to cut at right angles to that.
Right.
When you do that, now you get your strips.
Line.
You get your line.
You get a line.
Okay.
Right.
All right. So now suppose I want, because I do this often at home, I want to roast potato little cubes, potato cubes.
Oh, okay.
So it's like you mix it with some onions and garlic.
Absolutely.
It turns out great.
Yeah.
Oh man.
Oh, God,
okay.
yes.
How do I do that? Well, now I had a full 3-dimensional object. Now I just want particles out of that 3-dimensional object. So like 1 cut gets me the
potato chip.
2 cuts get me
a line.
Now I have to cut in the third dimension, and now I got my little cube. There
Right.
you go.
That's cool.
Okay. It took 3 cuts. However,
oh God, no.
there exists things you would cut An onion is otherwise a three-dimensional object, except think of it not in circular coordinates where everybody's an R. Think of it in spherical coordinates. What matters is, in those three-dimensional spherical coordinates, the onion is layered in R. So we have an R that's this size, and it's an R that's a little bigger, and R that's a little bigger,
right,
all the way out.
It just keeps going out.
It just keeps going out.
Right.
So if I want to cut an onion in all three of its dimensions, it's already cut in the R dimension.
Right, because it's layers going into zero.
That is a cut. That's effectively a cut.
Interesting.
Yes.
Okay. All right.
Yes.
All right, that's cool.
So if I want to make little cubes of onions, I only have to cut it twice rather than 3 times that you had to do with the potato. Okay?
Right. Because it's not pre-cut.
Because it's not pre-cut.
There you go. And the layers serve as the pre-cut.
As the pre-cut inside.
Okay, cool.
That's why it's easier to cut an onion than a potato. Yeah. For that reason.
Well, but potatoes don't make me cry. So that's one cut.
Okay, that's one cut. Your cut, you made one potato chip. A second cut, okay? And this